So, hello everyone.
Hey,
This is going to be thanks to Keith Conrad, who's going to give us a mini course on the infinite Galois theory.
yeah.
Keith.
Okay, um, so the topic, well, there is on the slides. Before I go further, I wanted to say that there were some lecture notes I wrote. They'll be slowly updated throughout the week that are on Piazza and also on the main CTNT page. Um, so I sent Alvaro a copy of the slides that I'm using. I don't know if he posted them somewhere. If not, maybe I'll try to do better on timing for this in the future. But um, in principle, these slides could be available for you to be writing on, but I don't know. We'll see what happens with that. If not,
I'm not sure. I haven't posted the slides, Keith. I think I've posted your notes on the website. But if you give me the slides, I can also post them.
I emailed them to you. Um,
Okay.
Maybe a personal email account of yours. Check, not your Yukon account.
Okay.
Yeah. All right. So after the lecture, after dinner, I'll check the Blackboard Collaborate room for my course to see if there are people who have questions there, and if I can remember how to access Zulip, I'll check that too. Okay. So yeah, so I want to talk about the extension of Galois theory to infinite degree extensions. In fact, in Sumia's talk, she was talking about the Tate module and its connection with, I don't know whether she said GQ or the Galois group of Q, and this is exactly what this is about. The Galois group of a field means the Galois group is basically its algebraic closure or separable closure. And so infinite degree Galois extensions is what I want to talk about. I'm going to review a little bit about the classical case and maybe do one sample calculation to remind you about that. And then I want to go forward and talk about what the what new phenomena happens in the infinite degree case. Some things stay the same, but there definitely are some new features. And we'll look at some examples today and the later lectures also, because you really only understand this stuff well by really understanding a few key examples. For instance, Liang this morning talked about the p-adic numbers, and you're going to see the p-adic showing up, that consistency condition for congruences modulo higher powers of p. You're going to actually see it showing up when you're trying to understand what an infinite Galois group is in a special case. And so hopefully by the end of the week, I'll be able to at least state and discuss some of the theorems that involve infinite Galois theory in kind of an essential way. So to begin, I should say, since this is a course on infinite Galois theory, I sort of am going to have to assume that you've seen ordinary Galois theory. It's just too much material to, but I'll have a little bit of a refresher about some key points. But if you've never seen Galois theory, enjoy. So ordinarily, one first sees Galois theory for finite extensions of fields. And being a finite extension, everything in the top field is the root of something with coefficients in the bottom field. And whoops. And Galois theory is about automorphisms. We look at automorphisms of the top field that fix the bottom field, meaning the all the elements downstairs stay unchanged. Okay, so when I say fixed, I mean pointwise. So the most basic example is complex conjugation, is an R automorphism of the complex numbers. It's additive and multiplicative, and it fixes exactly the real numbers. Other finite extensions, like Q adjoin the cube root of 2, its only automorphism over Q is the identity, because the cube root of 2 has nowhere else to go. And so although the field has degree 3, it's a cubic extension, the number of automorphisms is smaller than that. It's only the identity, not very interesting. And so the automorphisms of a field that's a finite extension of the base field is always a finite group, and its size is at most the degree of the extension. In fact, I think it divides the degree of the extension. And so the nicest situation you can be in is when that upper bound is achieved. So that's what being a Galois extension is about. One way of describing it, an extension where the number of automorphisms of the top field fixing the bottom field is exactly the degree of the extension. It's the same thing as being the splitting field of a separable polynomial with distinct roots. It's the same thing as saying the base field is exactly the elements that are fixed by all the automorphisms. Like in the cubic example, my second example on the slide, everything is fixed by the group of automorphisms, so it's not a Galois extension. And the other last property, these are all equivalent to each other, is the extension is separable and normal. If you know what that means, great. If not, don't worry about it. And when these conditions hold, we call the extension a Galois extension, and then we write the group of automorphisms of the top field fixing the bottom field as a Galois group L over K. So some people will actually call the automorphism group the Galois group all the time. They'll say the Galois group of Q adjoining the cube root of 2 over Q is trivial. This is a really, really, really bad idea. Don't do that, please. Okay? Just use the term Galois when it's actually a Galois extension. So the whole point about the Galois theory is that we have this correspondence going from the intermediate fields over to some subgroup. The subgroup is just the automorphisms that fix the elements in that field. Maybe more than the bottom field. And then given a subgroup of the Galois group, you can get intermediate field, namely what I call LH, the elements of L that are fixed by H. And the whole point is, right, that L over K being Galois means the elements of L that are fixed by the whole Galois group is exactly the base field. And so two standard examples.
Sorry, Keith.
Yes.
I just uploaded the slides and I put a link in the chat messages for if the.
Oh, in the chat window, I see that. Okay, so people can click on the link in the chat box for my lecture if you want to access the slides right now. Thanks. So the two standard examples that are worth reviewing if they're not familiar to you is cyclotomic fields. Adjoining an nth root of unity of order m, the Galois group looks like the units mod m, and the roots of unity get sent to a fixed power. So for instance, complex conjugation on the roots of unity is raising to the power -1. And so all the automorphisms look like raising to a power on the roots of unity, and when the base field is Q, all of them work. If the base field were the real numbers, well, R adjoined a fifth root of unity is still just the complex numbers. You only get a quadratic extension. So you get this big Galois group when the base field is Q. And that's an abelian Galois extension, and then a non-abelian example is given in the second example there. I'm not going to be using it too much, but that's kind of the basic example. Adjoining the cube root of 2 and the cube roots of unity, splitting field of x to the p -2, for instance. So the cyclotomic one for us is really going to be the more important one. So yeah, so the way that these, in the second example, the way that the automorphisms which are described, the way the automorphisms compose behaves just like the way those matrices multiply. This is an example that I work out in the course notes, so you can see it there. The automorphisms affect the roots of unity by a power, and they affect the pth root of 2 by a power that's just some exponent that's an integer mod p. So an example to consider, still in the classical case, if you adjoin a 25th root of unity, the degree over Q is phi of 25, which is 20. And so there's your degree 20 extension. And you can find some subfields. The fifth root of unity is a degree 4 extension. And the adjoining the square root of 5 is inside of there as a quadratic extension. And the Galois group is the units mod 25. Right? You take a number mod 25, and you act on the 25th roots of unity by raising to some power, and these are all automorphisms of the 25th cyclotomic field. And it happens that the group of units mod 25 is a cyclic group generated by 2. So when you do the Galois correspondence, the field goes over to the subgroup of elements that fix it. So the field Q goes over to everything, which is a subgroup generated by 2. Quadratic extension, you cut down by a factor of 2 to 2 squared. Zeta 5 is a 4th degree extension, quadratic on top of that, cut down by another factor of 2, 2 to the 4th. And then you go all the way up at the top, that's fixed only by the identity. And so it's easy, as someone commented in one of the earlier lectures, it's easy to write down quadratic extensions of Q. A more interesting thing to do would be to say, find a 5th degree Galois extension of Q. And so if we look at this extension in a broader way, we can actually work that out. So that's what I wrote here at the bottom. Let's find an extension of degree 5 of Q, degree 5 of Q. And so what we'll do is, if you want to get an extension of degree 5, you need to cut down the Galois group by a factor of 4. And so you look for elements of order 4 in the Galois group. Well, 7 has order 4 mod 25. That's related to the fact that 7 squared is congruent to -1 mod 25. Liang may have mentioned that when he was talking about roots of unity in the p-adics in the first lecture. I don't recall exactly. In any case, so if we apply the 7th power to the 25th roots of unity and add up the 7, 7 squared, 7 cubed, and 7 to the 4th first power, then we're going to get an element that's symmetric under a group of order 4. It will generate an extension of degree 5. And so there it is. There's the extension of degree 5. If you take that element alpha, you add up the powers using linear independence of the roots of unity, you find that this element does generate an extension of degree 5, a Galois extension of degree 5, and using computer algebra package that I know how to use. Alvaro always makes fun of me for using it. Paris, I found a 5th degree polynomial with alpha as a root. And so one can discover these things. And so there are all the different intermediate fields there. And so this is a kind of standard thing you do in ordinary Galois theory. Work out the Galois group, and then you can use the elements in the Galois group, if you really understand them, to figure out what the different intermediate fields are. Okay. So just check the box here. Whoops, on the screen to see if there are any questions. I've got to move to Sage. Yeah, I know Perry is in Sage. Someday, Alvaro. So anyway, yeah. So what's the deal with infinite Galois extensions? How do you define an infinite Galois extension? So you have to be a little bit careful, because if you look at the definition of a Galois extension, right, I had four properties that were equivalent. So some of them don't make any sense, like the first one, saying the number of automorphisms should be the degree of the extension. Well, this is not a good description if you want to do an infinite degree Galois extension. On the other hand, properties, or property 2 being the splitting field of a polynomial, you're not going to get an infinite degree extension by doing that. But properties 3 and 4 don't actually make any direct reference to finiteness properties of the extension. And so they actually both work. And so that's how you define an infinite degree Galois extension, is if you have an extension that's algebraic. So algebraic means it might be of infinite degree, but every particular element is still the root of a non-zero polynomial. So that kind of keeps it tied to the base field. Then we can list some examples of infinite degree algebraic extensions. So the first one is basically adjoining all the square roots of the integers. So you even have the square root of 10 coming from 2 times 5. So we join the square root of the primes and -1. So that's an infinite degree extension. That's kind of, people tend to visualize this as maybe kind of being like horizontal, because the different quadratic extensions are kind of sitting there kind of all in a row. While the next example, the p-th power cyclotomic extension, well, that's kind of more of a vertical type of thing. Okay, and so that might be kind of a vertical infinite extension, so to speak. And then you have these other examples, joining all the different nth roots of 2. That's a more complicated relationship. The cube root of 2 is inside the field joined by the 6th root of 2, but not inside the field joined by the 5th root of 2. So that's sort of more complicated. And then you can just adjoin everything, the algebraic closure of Q. And so these are all infinite degree extensions, but they're closely tied to the base field, Q in this case, because any one element is the root of a polynomial, lives in a finite extension. Any finite set of elements lives in a finite extension of the base field. And so what we're going to do then is use those properties characterizing finite Galois extensions that don't make a reference to a field degree, and that'll be our definition of an infinite degree Galois extension, potentially infinite degree Galois extension. So here's the definition, or rather theorem leading to a definition. So if you have an algebraic extension, could be like the ones on the previous slide, could be any of these, or it could be a finite extension, but it's not of direct interest right now. Then here are 4 properties of an algebraic extension that are all equivalent. First, that it's covered by finite Galois extensions. So assume we already know Galois theory for finite extensions. To say that the field is filled up by finite Galois extensions is the same thing as saying that the top field is the splitting field of a set of separable polynomials, not just one, but a whole family of them. Like, for example, here, the first example with the all the square roots. This is the splitting field of x squared plus 1, x squared minus 2, x squared minus 3, and so forth. I'm not going to multiply them all together to get one polynomial. There are infinitely many of these. So you can have an extension to the splitting field of a set of separable polynomials. Another possibility that's equivalent to them is saying the only elements fixed by all the automorphisms of L fixing K are the elements of K themselves. If something is in L and not in K, it's moved by some automorphism of L fixing K. And then we have the other property being separable and normal. In any case, these 4 conditions are all equivalent to each other. And this is how we define an infinite degree Galois extension. So concretely, maybe you go with the first definition. An infinite extension is Galois when it's covered by finite Galois extensions. And every element inside of L is inside a finite Galois extension that's also inside of L. So this helps us reduce things down to finite Galois extensions. And the Galois group is defined exactly like it is before. The automorphisms of L, this is all algebraic. There's nothing about limits or anything like that. It's just the abstract field automorphisms of L that fix all of K. Okay, we talked about that before. So, for instance, look down at the bottom of the slide, you can see that there's an example of adjoining all the square roots. The Galois group is simply all sequences of plus and minus signs where all these plus and minus signs, these come from the effect of sigma on square root of minus 1, square root of 2, square root of 3, and so forth. You just see, does it fix the 2 square roots of minus 1, or does it swap them? Does it fix the 2 square roots of 2? Does it swap them? If it swaps them, use a minus sign. If it fixes them, use a plus sign. And because these different square roots are kind of independent of each other, these choices of plus or minus signs, you can pick them however you wish. And any sequence of plus or minus signs really does give you an automorphism of the whole field. So this Galois group is just simply all plus or minus signs indexed by the primes and minus 1 there. Okay, so countable product of plus and minus signs. There's an example of an infinite Galois group. Seems pretty simple. Okay, nothing really huge going on there. It gets a lot more interesting if we kind of go vertical and look at the joining all the different fifth roots of unity. So each field is contained in the next one. And let's try to construct an automorphism. suppose I want an automorphism of the top field, okay, sigma, and I want to have it square the primitive fifth root of unity. What does that tell me about constraints on the 25th root of unity? Well, you see, the 25th root of unity, its fifth power is a fifth root of unity. If you want to, I suppose you could regard all of these as being e to the 2 pi I over 5 to the n, if you wish. So there's a consistency here, that if you raise one to the fifth power, it gives you the previous lower fifth power. And so what that means then is if you take sigma of both sides, then whatever you choose for where the 25th root of unity goes, its fifth power has to go to zeta 5 squared. And so if you send the primitive 25th root of unity to some exponent a, well then zeta 25 to the a to the 5 is zeta 5 squared, and zeta 25 to the fifth is zeta 5. So basically a has to be 2 mod 5. In other words, the 25th root of unity, its exponent could be 2, or add 5, or add 5, or add 5. 5 plus 12 is 17. If you added another 5, you would get 22. 2 add 5 is 7, add 5 is 12, add 5 is 17, and another 5 is 22. And if you add another 5, you get to 27. The 27th power is the same as the second power. Anyway, the upshot is that you got a constraint. The constraint is the power has to be something that's 2 mod 5. And if you call this zeta 25 to the a, well, the 125th root of unity is going to have to go to something whose exponent will have to reduce to what you picked for the exponent on a. And remember, a had to be 2. So there's a rolling consistency property. And this last example, this goes to zeta 625 to the c. The c, if you look at the consistency, has to look like b mod 125. And so you see, whatever choice you make along the way, the later ones are affected. And so this is just like what Liang was talking about with p-adic numbers. In other words, the collection of exponents here is a system of numbers modulo 5, 25, 125, 625, all these higher powers where every new exponent is constrained to reduce to the previous exponent modulo the previous power of 5. And that's the only constraint at all. Okay? As long as you hold to that, you can build an automorphism by selecting exponents randomly as long as you lift your exponent to the next power of 5 and don't just pick it at random. So you have this system of constraints. And so in fact, this Galois group, if you think about it in terms of the effect of the exponents, is essentially 5-adic integers, with the proviso that the lowest one cannot be 0 mod 5. Can't send sigma of zeta 5 to the number 1. So the exponent at the beginning has to be 1, 2, 3, or 4. But after that, you can kind of pick it consistently however you wish. And so there's an example of an infinite Galois group, all the collections of exponents. Okay? And so this is what I have on the next slide, that as long as you constrain yourself to send the 5 to the nth order root of unity to some exponent, it has to be consistent with the previous exponent, and you just have to make sure that the very first one is not 0. And otherwise, you just start lifting however you wish. And so basically, the Galois group of the 5-power cyclotomic infinite extension of Q is the 5-adic integers that are invertible, okay, whose first digit is 1, 2, 3, or 4. And so here's an example. Start with 2 mod 5. You want the 5th roots of unity to be squared. You could decide you want the 25th roots of unity to be raised to the 7th power. Then you could decide you want the 125th roots of unity to be raised to the, 75 plus 7 is 82? 75, yeah, something like that. Anyway, and so you could write out the effect on the 5th power roots of unity as raising those numbers to a single 5-adic integer. You see, if I took, for example, the 25th root of unity, look here, and I raised it to a 5-adic integer, what does that mean? Because the powers of 25 and 125 multiplicatively are trivial on zeta 25. If you formally multiplied out all those powers, all the higher 5 powers would disappear, and all that really matters, all that you're left with, is zeta 25 to the sum of the first 2 terms before you start hitting the 25s. And so that's zeta 5 to the 7. Or as another example, what would it mean to raise, time to open up slides. Let's add a page. So if I wanted to raise -1 to a 2-adic integer, oops, sorry about that. Formally speaking, it's an infinite product, but all of these other terms, they're just 1. And so all you're left with at the end is -1 to the C naught. That's the meaning of -1 to a 2-adic integer, or I to a 2-adic integer. Formally, you multiply it out, but these higher powers don't matter because I to the 4th is 1. And so all you're left with is I to the C naught plus 2C1. You could add on a finite number of extra powers of 2, but they're not going to have an effect. So this is, you can think about p-adic integers, p-adic units, being applied directly to the p power roots of unity. In this case, here we're talking about 5 power roots of unity. You apply them as the exponent, and everything makes good algebraic sense. Okay, so you can make the p-adic integers invertible under multiplication act on the p power roots of unity, and there's an interpretation of an infinite Galois group. Okay, maybe I should stop to see if there are any questions. I don't see anything written here. I don't know if I'm not looking in the right place.
I don't see any questions. Any questions so far? Let's see if anyone chimes in.
I don't know what other channels I'm supposed to be checking. I don't use Twitter, so don't ask me questions there.
We have one question from Kirk. So let me
Yes.
make sure. Okay, so Kirk, you should be able to speak.
A couple of slides ago, you mentioned that joining the various nth roots of 2 was not a Galois.
Oh, yeah, I'm sorry.
I was
I kind of
curious
skipped over
why
that.
was.
Yeah, so right, so we had this field adjoining all the different nth roots of 2, and that's not a Galois extension. And I mentioned except that, and so yeah, let's talk about that. I completely forgot about that. So let me see where that occurs here on the in the margin notes. This is the tower. I think that's, where is that? Here we go. Okay. All right. So yeah, so let's discuss that, and let's use this as an occasion to let's go with pink. Okay. So Why is the union? So think about this inside the real numbers, compatible nth roots of 2. Why is this not Galois over Q? And the reason, or a reason it isn't, is you can think about it inside the real numbers. And so the nth root of 2 is inside the field, but the non-real nth roots of 2, non-real nth roots of 2 are not. So here, this is why I definitely need n to be bigger than 2, but we're taking the union over all n. Okay, and so so for a Galois extension, anything that's in there, all the other roots of this minimal polynomial over the base field have to be in there too. And so here, the fifth root of 2, there's only one fifth root of 2 in this field. You need 5 of them if this is supposed to be a Galois extension. If it was a Galois extension containing a fifth root of 2, it would have to contain 5 fifth roots of 2. Okay? Does that answer your question?
There was another question, Keith, which is, when you say infinite, do you mean countably infinite?
So when I talk about an infinite degree extension, I'm thinking about how large of a degree can you have? It sort of depends upon the cardinality of the base field. So if the base field were, let's say, the rational numbers, then the algebraic closure only has countably many elements in it. And so you can really only have a countable number of extensions. But if you have some really huge field, not related to, like, maybe the rational functions with complex coefficients, then that's much more complicated. So for my purpose, infinite degree just means not finite degree. Okay, you could have, not over the rational numbers, but over suitable other fields, you could have a really, really large, the algebraic closure of some field, big fields of characteristic 0, could be uncountable degree, I think, because it's hard to, I think so, yeah. But in any case, for our purposes, infinite just means not finite. Okay. So going back to, we were discussing, how do you actually construct an element of an infinite Galois group? Look, I already gave you some examples. I showed you the kind of multi-quadratic adjoining all the square roots, and that was pretty concrete. And then I showed you the pth power roots of unity, and that was pretty concrete. Well, if you've seen p-adics, then you say, oh, okay, I'm just picking exponents that are modularly compatible with the earlier choices. So you kind of have a good concrete model for what the Galois group looks like. But unfortunately, in general, you can't really expect to have formulas for the elements in an infinite Galois group. And so what we have to be relying on is a basic theorem that involves the axiom of choice, which says that if you have a Galois extension, and so let's say this is a Galois extension, possibly of infinite degree, that if you have an automorphism of E that fixes K, then you can find an automorphism of sigma that fixes K. So you pick an element phi in there, and you want to have an element sigma whose restriction to E is phi. So there's kind of lifting of automorphisms. If you have any Galois extension in between L and K, for example, a finite one, where you can kind of write down formulas. Oh, I want to send this root here and this root here, and these elements generate the intermediate extension, and so that kind of everything has been determined. But then there's an enormous there's an enormous non-constructive aspect in saying that you can actually extend these automorphisms in bazillion ways to the entire Galois extension. Okay, so the proof of this is, I made it an appendix in the course notes because it takes quite a while compared to the statement of the theorem to pin down all the details. So if you've never seen the axiom of choice or in algebra more like Zorn's lemma used, this could be used to show vector spaces, non-zero vector spaces have non-empty bases, and functional analysis, the Hahn-Banach theorem. And so Zorn's lemma is used a lot in abstract algebra for non-constructive existence theorems, existence of an algebraic closure. And so this is yet another one. And so I think it's worthwhile to kind of go through the proof yourself to see how this happens. How do you construct an extension? And because it uses Zorn's lemma, the fact that automorphisms at kind of a finite level can be lifted in a lot of ways all the way to the top. This is the main reason, the reason that we know non-trivial elements of Galois groups exist. You give a finite amount of data at some lower basic level, and then by Zorn's lemma, you can find an extension of it all the way to the top. And so you have to keep in mind that you do not expect formulas for these things on the whole field at the top. So you could take the conjugation on Q adjoining the square root of 2. This can be lifted to an automorphism of the Galois group of Q bar over Q. Unfortunately, you cannot describe a formula for such extensions. It's certainly not the identity function. It's certainly not complex conjugation, because look, it swaps the two square roots of 2. And you cannot write down formulas on all of Q bar other than basically those two. But these things exist, and it's really important. And so you're kind of always dragging along this non-constructive existence of these automorphisms. Or take the 7th power on the 25th roots of unity. This can be extended to an automorphism of Q bar in a ton of ways, but you can't write down a formula for this. It's not going to be the 7th power on everything. 7th power is an additive in characteristic 0. And something else to emphasize is just because at the little finite levels, like Q adjoining the square root of 2, Q adjoining the 25th roots of unity, that these automorphisms are of finite order. Conjugation is order 2, raising to the 7th power on the 25th roots of unity is order 4. We talked about that. When you extend these to Q bar, they're going to be automorphisms of infinite order, because the only elements of finite order in the Galois group of Q bar over Q is the identity and complex conjugation and conjugates of complex conjugation in the sense of group theory, YX, Y inverse. And those have order 2, and they fix the real numbers. And so, in any case, the point is that you just cannot expect we use these elements all the time when we're working with infinite Galois groups, but it's hard to write down a formula for them. In the last lecture, I will show you that there are a lot of elements for which you can write down a kind of formula. And these are really important in number theory, called Frobenius elements attached to prime ideals. But they have infinite order, and so you have to kind of keep that in mind. When you go all the way up, you lose a lot of control over things. Okay. I don't know if there are any further questions. Ask about that.
Actually, maybe related to that on the previous question, somebody was asking, but
I see.
Isn't that infinite product of plus minus ones uncountable?
Sure. Yes. The Galois group is uncountable. I'm sorry, I thought you meant is the degree of the extension uncountable. Oh. No, these infinite Galois groups, we'll see by the end of the lecture. Oh, they're always uncountable. Always. Yes, I'm sorry, I misunderstood. Yes, the Galois groups are, if they're either finite or uncountable. I'm sorry, I thought it was talking about the field degree. That could be countable or uncountable. But yes, the Galois groups will in fact be uncountable. That is true. We'll get an understanding of that later today. So I have 10 more minutes. Okay. So yeah. So let's talk about the Galois correspondence. Okay. So please keep in mind there is no analysis here. We're not talking about continuous automorphisms. There's no limits. Okay. We're just talking about a field extension, that's algebra, and a field automorphism, additive, multiplicative, 1 goes to 1. Everything is just purely algebraic. Okay. And so you can talk about the Galois correspondence from finite Galois theory. Given a field E, you go to the subgroup of elements that fixes it. Given a subgroup H, you go to the elements fixed by H. And so this correspondence in finite Galois theory makes sense even if the extension is of infinite degree. So as I wrote in the 2 bullet points, given an E, you get a subgroup, the Galois group of L over E. And given a subgroup H, you get a field of elements fixed by H. And so you can iterate the process. Start with the field E, get a subgroup, automorphisms that fix E, that's what I have in red there, and then go back to a subfield, the elements that are fixed by the automorphisms that fix E. Certainly includes E, and in fact, it turns out it includes nothing more. Although the proof of that involves this Zorn's lemma stuff I was telling you about. But so one aspect of the Galois correspondence works just the same, even if it's not a finite extension. Going from a field to a subgroup, back to a field, you get back to where you started. Okay? And the proof of it needs or uses finite Galois theory. Okay, so some of these results in the infinite case might sound like, oh, it's just like the finite case, but we're going to use, one uses the finite case. And in the course notes, if you read the proofs, you see I kind of put in italics, by finite Galois theory, we can generalize the result. So the real problems start if you start with the subgroup. Start with the subgroup of the Galois group, go to the elements that are fixed by it, and then go to the automorphisms of the top field that fix the elements fixed by H. Well, the elements of H fix the elements that are fixed by H. However, you can find more stuff. There can be more things that fix the stuff fixed by H than just H itself. So it's like, what the heck is this? Too much repetition here. The bottom line is, if you iterate the Galois correspondence starting from a subgroup and come back to a subgroup, you might wind up at a bigger subgroup. Okay, as I say at the bottom there, you can have 2 different subgroups, in fact, which correspond to the, when you iterate it twice, you wind up at the same subgroup that's different from both of them. Okay, so I see people are asking about the annotated slides. I mean, I'll post these later on, so I might make some edits afterwards, but yeah, I can post the slides later. So, so let me show you an example where we wind up with, here we take the 2-power cyclotomic extension, and I'm going to give you 2 subgroups of the Galois group of the big cyclotomic 2-power extension. So what is this group going to look like here? So this group basically looks like invertible 2-adic integers. Whoops. Whoa, hold on a second. 2-adic integers acting on the 2-power roots of unity as exponents. I showed you an example of that before with raising I to a 2-adic integer, raising -1 to a 2-adic integer, okay, a 2-adic unit. And so, so there's an example of some of the intermediate fields, zeta 8, zeta 4, down the bottom, zeta 2. And so I'm going to let sigma A be raising to the power A. A here is an integer mod 2 to the n that's odd, so that raising to that power doesn't change the order of the root of unity. And so here I have 2 subgroups. Ooh, I can use my, here we have 2 subgroups. Whoops. So what are these 2 subgroups? Stop broadcasting. No, I don't want to. Is everything still okay, Alvaro?
Yep.
Okay, good. Okay. So what are these subgroups? The first subgroup, they're cyclic groups generated by the 5th power map and the 13th power map on all the 2-power roots of unity. Okay, that's what I have here. Okay, so one group is generated by raising to the 5th power over and over and over again, or inverting that, raising to the 1/5 power, modulo powers of 2, 2-power roots of unity. And then there's 13th power. These are not the same subgroup. In fact, they intersect trivially. They're infinite cyclic subgroups of the Galois group. And if you thought they had something in common, well, each group is cyclic, infinite cyclic, so it only has 2 generators. So if you imagine the 5th, raising to the 5th power and raising to 13 or 13 inverse power, they'd have to be the same. But if that's true modulo every power of 2 on the exponents, then 5 has to be 13 or 1 over 13, which is not true. So in any case, these subgroups are distinct. They intersect only trivially. But it turns out that they actually fix, they fix the same stuff. So the different subgroups fix the same stuff. How does that work? Well, the point is, it's a kind of fact of modular arithmetic, that the number 5 and the number 13, they're both 1 mod 4, and so they certainly fix I. And it turns out, that's what I have in the box, that modulo powers of 2, 4, 8, 16, 32, they generate the same subgroup, modulo every power of 2, if you take their powers. And so if you look at any finite layer, Q adjoining the 2 to the nth roots of unity, the powers of 5 and the powers of 13 mod 2 to the n are the same subgroup. So they're going to fix the same elements of Q adjoins zeta 2 to the n. But if you fix the same elements at every Q zeta 2 to the n, everything is in one of these, right? Any element is in some finite extension, and these 2-power roots of unity kind of filter everything is inside one of them. And so the fixed elements have to occur at a finite level, and that makes it fixed by the powers of 5 and the powers of 13. So they fix the same stuff. In fact, what they fix is exactly Q adjoin I. And so even though the subgroups are different, they have the same fixed field. And so this is totally different from the finite case. Okay, so that's a surprise. And so the problem is that there are basically too many subgroups. Okay, so Dedekind, back in 1901, was actually looking at this very example, p-power cyclotomic extensions, and he realized that you have this strange stuff is happening when you try to see if the Galois correspondence works. And he suggested that maybe in this infinite group, there could be a kind of a continuity involved, but he didn't really give details. And only almost 30 years later, Krull created a topology on the Galois group, which has some amazing properties. So first of all, it behaves well for the operations in the Galois group. They're continuous. And it makes the Galois group into a compact Hausdorff topological group. I'll talk about that next time. The topology is very different from the real numbers. It's totally disconnected. In the finite case, the topology is discrete, and that's why you never noticed it in finite Galois theory, because the whole thing is a finite discrete group. Topology is of no interest. The subgroup corresponding to every field is a closed subgroup for this topology. And if you iterate the operation of the Galois correspondence starting from a group and going to a field and coming back to a group, you always get back to the closure of your original group. And those two groups that I showed you before are not closed, but they have the same closure. And so if you focus on closed subgroups and all intermediate fields, then the Galois correspondence works very well. Okay, and so I have not told you what that topology is. Since we're already at 4:49, I think this might be a good place. This is probably a good place to stop. So we'll start next time and explain what the topology is, and at the end see in some examples how it lines up very nicely with, for example, the p-adic topology or the product topology on those Galois groups that we calculated before. Okay, and so we'll stop here, and we'll continue next time from the next slide. Are there any questions?